Đi vì sao? Có tới đây không? Có chụp ảnh đẹp không?
Anh đi anh.
Thế?
Anh đi anh.
Chụp ở đây này. Góc đẹp chưa?
Hả?
Góc đẹp chưa?
Rồi. Ánh sáng này.
Chỗ là tắt đèn đấy.
Xịn.
Phần lờ.
Hả?
Phần lờ. Đã lấy đồ ăn vào chẳng cho nó lên đường.
Ủa? Này.
Lại đây.
Sẽ đánh sau lên một.
À. Sẽ lên không? Ok.
Tắt đèn rồi thì đèn là khi.
Tắt đèn chạy điện. Ui đây mất chỗ rồi. Thì lấy sẵn đi chắc nó ngồi trong tay.
Ủa sao hết à?
Đấy.
Ủa hết à?
Không thể hết.
Hết chưa thì bắt đầu à?
Không hết đâu ra cũng còn. Rồi là trong một tiếng không làm gì. Chơi à.
Okay, Jake set up the stream remotely, so I think it's streaming right now, actually.
Oh, okay. Yeah, so I'm wondering if it's recording this screen or this screen.
It should be recording whatever the projector is.
Okay. Okay, thanks.
Just because Jake is doing it remotely, we just need to make sure that we turn it off before the closed session. So like I have to text him for the closed session.
Yeah, but I don't have to press.
No.
Okay.
We are supposed to forget the button. That's what Jake told me.
Yeah, it should be flashing red. Yeah. Hi, Rich.
Hello.
This
All set?
Yeah. Just
I
waiting.
see
for-
good stuff out there. Actually, I'm supposed to sit at this part of the table.
Này em xử lý ổ bảo này.
Không phải cho ông đi đâu chị.
Đúng rồi.
Sao lại cho ông khác? Nên ông cho phải chịu.
You guys should take something outside.
What?
Yeah. You yeah, Drago. Just Jenny, you can take something outside.
What?
Food and coffee.
Oh, yeah, thanks. I'm good.
Hi, Tam. Hi, Tam. Yeah, we are about to start, so I just want to call you first. But yeah, so I put the laptop like this. You see my screen?
Yes, and you sent me the slides already, right?
Okay, yeah. So that will be the last slides we are going to go over.
But yes, so I will.
Yeah. So the committee members haven't come yet, so probably 1 or 2 more minutes.
Okay,
Okay.
sounds good.
And yeah, Rich is here. Is here.
I just want you to know that bribes aren't going to get you passed,
Okay.
no matter
Yeah,
how
this
good
is
they
right.
look.
The
Hi, great.
time is here.
Tam's here? Okay, hi Tam.
Hi, how are you? I can't see you.
I know. I'll have to move over here so you can see me. Hi.
Hey.
Hi,
nice
hi.
shirt. Nice shirt.
Thank you.
Love it.
Have you guys stopped having snow there yet?
Just like about a week now.
Wow.
Not that we love it, but we are used to it.
Yep, that's good. You like Denver? You've been there now for a while.
Yeah, I've been here for about 6 years now, right? I'm in Boulder, so now
Right.
I'm in Boulder. So it's,
The Denver area is.
Denver area, yeah.
Right.
You come here skiing often?
No, I usually go to Utah where they have real snow.
Yeah, that's a better one, yeah. They
But
have real snow.
my son is at Golden though, at Mines, doing a physics degree. And
Nice.
so I see
which year
pictures-
is he in?
pardon me?
Which year is he in?
Oh, he's just starting a PhD. He's got a master's already.
Ooh, nice. So you will probably come down more often.
I will come out more often. I get pictures of him sand surfing, with a snowboard on sand, which I thought was pretty cool.
Nice. But there's a nice sand dune somewhere, like 3 hours down.
Yeah, that's where they went to go sand surfing. It was great.
You know how to enjoy life.
And good. It's good. How about you? How's the kid? How's your
Been
family?
okay. Well, looking. Yeah, my kids in Vietnam, they go back there once in a while.
Oh, that's good.
Yeah. We work on a lot of health stuff, healthcare.
Yeah, I'd like to hear more about it.
Yeah.
I have to stop by and see you when I come to Golden. You're right next to Golden.
Yeah, it's like 20 minutes away.
Right.
So it's very close and no traffic.
No traffic except for all the Teslas. I couldn't believe the number of Teslas around there.
there.
It's fantastic.
Right.
Okay, Viet, who else is coming, Viet?
Marco, Wade, and Nguyen.
Oh, okay.
Wade is here already, so for digging.
Okay, so we have to turn this so that he can see you.
That's all the
Yeah.
presentation.
Okay,
Yeah.
just get that lined up for him.
So what's your plan after this, Viet?
So I'm going to Texas next month, next week actually, to start a research engineer at Samsung Research.
Oh, cool.
Yeah.
Cool. Which group? Which group?
So the name of the group is 5G and the next generation mobile experience group.
Next generation mobile experience. Nice, nice. So they do a lot of dancing, and so you are doing two things, right? One is that augmented reality,
Yeah.
and the other is this,
Yeah.
right? Some communication stuff.
The next generation mobile experience will be faster dead batteries. More data rate, more amps per the final power amplifier, more dead batteries. Batteries aren't getting better if you don't want to use ones that blow up.
Right. So your slide hasn't changed, right, Rick?
My
I remember
slide doesn't
that,
change, there are no new batteries.
8 years ago, what was it? 8 or 9 years ago, you had that slide. I'm talking about,
I
yes.
saw this
Right.
slide.
Keep going, but
The data rate,
batteries are bad.
batteries die. So
Right.
it's,
Mm.
and faster data rate, the computer doesn't use more power necessarily, although we're running out of the Moore curve. But the power amp uses the same amount of power. If you run the data
Right.
rate faster in the power amp, you run your battery down faster.
That's right. Mm.
So it's gonna be fun.
There will be there will be non-linear improvement, right? There will be a technology, there will be like breakthrough, and it will have a leap. Just like with Moore's law, it's the quantum computing might be
Sure,
that, right?
that's a good way to think, but I'll point out that people still build houses out of wood.
Not the thing, but that's the way you hope, right? That's what
Yeah.
my hope is.
They still build houses out of wood and cars out of steel for good reason. They're cheap and they do the job.
Right. Until we can come up with some better material, like cheap,
Mhm.
all the nice quality you
Sure.
want.
Yeah, let's make cars out of magnesium or titanium. Those burn really well. So what are you doing in healthcare?
So I built a lot of wearable devices and mobile devices for measuring vital signals. So and I found 2 companies to commercialize them, and it's just so much work. If you remember, 4 years ago I talked about the in-ear sensing technology.
Sure.
We tried to build a device or platform that's called earable, and the company also called earable. that earable, you get the name, right? Like,
I got the name, yes.
Earable. What earable?
Very,
No.
very cute.
Thank you, thank you. You got it. Many people are like, why you have that name?
Of course, the question is, does it work?
It does. So we were able to use that. So the nice thing is that it can capture your brain signal, eye signal, and muscle signal very accurately when you don't move a lot. For an example of when you're not moving a lot is when you're sleeping or when you're sitting and work. So our first product we're trying to build is monitoring your sleep quality and then improve your sleep quality. So the product is a smart earphone that can capture your brain, eyes, and muscle signal all at once when you're sleeping or when you're sitting, working, so that we can monitor your sleep stages or if you're fatigued or focused. And from that, we will send in just some coaching and some audio acoustics, either sounds or coaching techniques that improve, reduce the latency to sleep or help you to sleep faster. And
Okay.
also
Sleep
send
faster?
out etc.
Are we talking about sleeping faster? Were you serious about saying that? Get everybody so they can do it in 4 hours, what used to take 8?
Oh, no, I mean, that is so what we try to make the sleep latency is shorter, meaning
Okay.
it might give you 15 minutes during lunchtime so that you can take a power nap. We want to make it super power nap, right?
Sure, that's what grad school was for, to learn how to do that.
That's what Russian
Exactly,
literature
right?
is for.
So, except that here, like you have an earphone, and instead of just sitting in the desk and put your head down on the keyboard like a grad student.
Sure, that works. Does it affect your hearing?
So
The unit?
Two form factor. One is in ear and around. The other is behind the ear. So behind the ear we'll use a bone conductant a microphone, so it doesn't. Sorry, speaker. So it does not block your hearing. But the in ear would block your hearing.
Yeah.
Yeah. So which is good for sleep.
You need to drill another hole in people's heads so that you can install it without affecting their hearing.
Right. That's what those hearing aid people do, right? They drill a hole and they put the device in your head and they help you to hear better now. What do you think also along that line?
Yeah. That's going to be wildly popular. You can get your Audible Facebook feed right directly into your brain.
Right. Yeah.
Now that will be a boon to humanity.
Yeah. Boon.
Where's Marco?
We're still talking.
I saw him walk in.
Yeah.
Oh, he's here. Okay.
Yeah.
There's some interesting goodies out there.
Yeah, I just had.
Oh, if you don't partake, you can't be properly bribed.
Hi.
Hi, Marco. Hi.
Okay, I got everyone here. Yeah, Marco is.
Nice.
Hey.
Hi everyone.
Hi, Tom.
Hi Marco. Hi Wade. Right there as well. Hi Wade.
Hello.
Amazing that we get everybody together in the
Ying
summer.
Ying. I can't see Ying Ying. Hi Ying.
He's getting food.
Oh, yeah.
I know Ying is good. She's
Outside the
good.
room. But that's Rich just walking by.
Yeah.
Okay.
But we have to turn it around so he can see.
Yeah. Okay, I'll turn
Yes,
around.
you turn around.
Okay.
Keep on forgetting to take them all.
Can you see okay?
I ran over.
Or is, or
I
is,
can, I
okay.
can see it well, yes, and I also have the slide here, so I will just flip through the slide
okay, good.
as you go. Thank you.
Big one.
Yeah. How's your commute?
Getting better. It's more flexible now.
Good.
You work from home sometimes.
See, it's like an incentive if you can solve the smart transportation problem, then your commute gets like really a lot better, so get to work.
There you go. Yeah, dog food, that's the thing.
But there's no better solution than just staying at home, so.
That is true. So what do you do these days?
Little, less than I wanted to. I love being home more.
All right, perhaps we just get started. I think King will be walking in a moment. All right, you all know Viet. This is a thesis defense. Let's go ahead.
Okay. Maybe just turn on the light. Okay, thanks for me. Okay, good morning everyone, and thank you all for coming to my PhD dissertation defense. And the title of my thesis today is Communication Sensing Techniques for Smart and Seamless Human-Environment Interactions. During my PhD, I have worked on several aspects of ubiquitous computing, so I would like to start this talk with some primer on this field. The field ubiquitous computing is pioneered by Mark Weiser, a research scientist at Ceres Park. His vision of ubiquitous computing is stated in his famous paper, The Computer for the 21st Century. And that vision is the most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they are indistinguishable from it. So this is a great vision of the future of computing, especially in 1991 when the paper was written. So when we look at the landscape of technologies that we have today, we can say that Mark Weiser's vision has largely come true. Ubiquitous computing devices and applications are everywhere. They reach every aspect of users' life and operating in the background, their activities, providing useful services without getting into the way. Some applications we are now getting used to, for example, wearable devices, smart home building, smart cities, and self-driving cars. And some research are still ongoing, for example, smart fabrics, smart dust, and drones. And even the current exciting research on artificial intelligence is also aiming at the vision of ubiquitous computing. We are developing AI that is a human-like assistant to us in our daily life. So, however, when there are still several missing components in realizing the invisible aspect of ubiquitous computing, the user still need to give explicit attention to this should be the device. For example, the person needs to pull out his smartphone to capture a QR code that stores additional information about the product. Or the user needs to explicitly enter the PIN code in order to be authenticated to the phone to continue interacting with it. And some device operation cause interruption to the user's workflow. Even for the more immersive devices like the augmented reality headsets, the user still sometimes need to stop what they are doing with their hands to swipe on the device or perform the on-hand gestures to control the device. And some ambient sensing techniques require complex infrastructure setup. For example, cameras, RF device, and infrared motion sensing. They require installation of additional sensors in the environments. So the deployment of large number of devices to cover an indoor space would incur significant extra costs. Also, there are still some security and privacy issues in some of the current human-to-environment interactions. Cameras being used for monitoring indoor user activities can cause discomfort because user nowadays increasingly concerned about the privacy. Or for authentication purpose, for users with the devices, some methods using wireless signal, for example, Bluetooth or NFC, they are susceptible to eavesdropping or man-in-the-middle attack. So the goal of this thesis is to develop communication and sensing methods with particular focus on the above problems for realizing smart and seamless human-environment interfaces, interactions. This method will follow these design principles. First, they avoid interruption to the normal workflow. They happen in the background without the user's notice. Second, the design would have minimal instrumentation both in the environments and on the human body. Either users are not required to carry any devices, or the wearable devices are already widely adopted. Third, when we leave the communication and sensing happens in the background in automatic mode, built-in security and privacy primitives are highly desirable. So this table shows the overview of the 4 systems that I have worked on during my PhD. They are built on 2 modalities, visual light and capacitive coupling. In particular, for the 2 communications projects, textual code and body-guided communications, I try to embed the message in these modalities to enable information exchange when the user look at an electronic display and when the user touch a device. For the 2 sensing projects, EyeLight and HandSense, we utilize the sensor arrays of these modalities for tracking people's indoor movement and then tracking the small finger movements that can be used for controlling augmented reality head-mounted devices. Okay, so now let's start with the first project, textual code, high-speed flicker-free screen-to-camera communication with spatially adaptive embedding. So wearable glasses are becoming more mainstream, and they are usually equipped with camera that aligns well with what we are looking at. And also we have pervasive use of electronic displays in public areas. The motivation for this project is that can smart glasses capture side information from the display screens the users are looking at? For example, by just looking at this electronic advertisement, the wearable glasses can help us quickly capture all side information for later reference. So the most common approach for this task is using QR code. It has become common in screen-to-camera communication for different applications like getting information for the product, from the TV show or pairing devices. However, they have some disadvantages. The code occupies a portion of the screen. So when in use, it blocks specific contents of the video or image. And also the code is static, so we can only embed a fixed message of a fixed length. And it also has a low throughput. The code is small, so we have less throughput and requires closer distance to the screen. So to address the limitation of communication through QR code, embedded screen-to-camera communication is desirable. The basic idea
So
is...
how low is the throughput? I mean, all right, so quick advice. You're giving your PhD defense. You're gonna make a statement like low throughput. Quantify that for your PhD evaluation committee, all right? Low throughput 1 bit per second, low throughput 10,000 bits per second. Some of us think that 2 gigabits per second now is low. So tell us what low throughput is. Give us a context.
So here, the user would need to. So this is the QR code, and the user camera to point it to it, and it requires some time to process, do computer vision on this. So that this should be only the order. And also it depends on the amount of information stored in this. So that should be maybe in the order of tens or 100 bits per second.
Okay.
Yeah. Yeah. Thank you for the comment. So, so the embedded screen-to-camera communication would have user experience normal full screen content without any distraction of the code, and the message would be moved to another channel that is imperceptible to the viewers, but the camera should still be able to pick it up. Now the message can utilize the full display real estate, and it is decoupled from the screen contents, so we can improve the throughput significantly compared to the QR code. In order to realize this communication, the challenges here is to modulate the message in a way that it doesn't cause any distortion to the user, but still provide high enough throughput channel to deliver the message. So to address these challenges, we designed a new encoding method called texture code. This design is a combination of several techniques belong to the temporal domain and spatial domain. On the temporal domain, we use Manchester encoding, and on spatial domain, we have a spatially adaptive embedding and simple pixels method. Each component in this design is utilized to address each corresponding factor that affect the flicker perception, which is frame rate and image contents and sockets. By using this component, our design can help reduce flicker, and it also combines multiple dimensions of coding opportunities in order to increase the communication throughput. So flicker perception, flicker is a common artifact in embedded screen-to-camera communication. So we want to verify the factors that affect the flicker perception that are known from literature. The first factor is frame rate. So in this experiment, we placed 2 uniform grayscale blocks side by side. The left block has a fixed intensity, and the right block flipping between the darker and brighter values. What we observe is that when we flipping the right block at 120 frames per second, the right block would be average to the human eyes and look the same as the left block with some value of adding and subtracting the pixel values. So this is because the human eyes cannot perceive the change of light at very high speed. So the first hint for encoding is that we should use high frame rate videos to embed the message. The second factor is image contents. We observe that intensity modification in smooth regions like this road is more likely to cause flicker in the texture region, like in this building area. And the third factor is sockets, which are rapid eye movement that abruptly change the point of fixation. In this experiment, when the two neighboring blocks are modulated with different phases, one go from black to white, and the other is from white to black. When we look at these blocks and we change the point of fixations, then we still will be able to see the flicker at the edges, even at the high frequency as 120 frames per second. So, but we observe that by separating the blocks with some distance, it can reduce the flicker effect at the boundary. So this is how to avoid sockets. So the temporal embedding aims at the frame rate. Each video frame is divided into checkerboard blocks, and each block carries 1 bit of information. From an original 30 frames per second, we created a 120 frames per second video by duplicating each frame into 4 frames, and these 4 new frames are then used to embed the message. We choose Manchester encoding. Bit 1 is denoted as high to low intensity, and bit 0 is low to high intensity. The pixel values inside the high block is increased by alpha, and the pixel values inside the low block is decreased by beta. And at high speed display, we can choose alpha and beta values, so these blocks will be averaged to the original pixel intensity, so the viewer will not see the difference in the video contents.
So I would like to understand the sequence of events and where is the actual encoding being done relative to the creation, compression, transmission, delivery of this video.
So this
So
is
30 frames per second, that's what, NTSC or PAL, right?
yeah.
Alright, so that's like an industry standard for basic video coding.
Yeah.
Alright, now you're going to embed at 60 frames per second, then you're gonna code it up to 120 frames per second.
Mm-hmm. Right.
So now you've quadrupled the amount of bits, right? Because in order to get 120 frames per second, now you have 120 frames per second as opposed to 30 frames per second.
Yeah.
So, are you going to then send 4 times as much video? Or are you going to do this encoding?
No. So this 30 frames per second, but we are playing this on the 120 frames per hertz, 120 hertz refresh rate video screen. So the video would be the same. So it on 120 hertz screen refresh rate screen. So this 30 frames per second would 1 frame would be remain the same for.
I got that. So now you have a message that you want to be encoded. All right. I have a message I want to be encoded. Here's a video. It's at 30 frames per second.
Mm.
All right. You're gonna send that 30 frame per second video to a screen that's gonna display at 120 frames per second.
Right.
But I've got a message over here. All right. So where is that message being integrated with the video in order to go to the 120 frame per second screen?
Yeah. So for this project, we so all the processing is offline. So we have the video, and then we extract the videos, the video into frames, and then use that frame, duplicate it into 4 frames, and then process each frame separately by changing the pixel intensities of each frame, and then
So with
merge
this-
it back into 120 frames per second videos.
All right, so question is, would this necessitate like an additional application to be developed that allows me to send the message I want to show up on Marco's screen? Marco would run Wade's player, all right? Wade's player takes the video, takes the message, it takes the 30 frame per second video and takes the message and then modulates it through these 2 methods and then sends it to his screen at 120 frames per second. Is
Yeah,
that
so-
what would happen?
Yeah, that it should be a separate application for merging
Right.
these 2.
That would have been helpful to understand. I got it, okay.
Okay. Yeah. Okay, so that is for the temporal embedding. Then the spatially adaptive embedding will try to find blocks that have low flicker when encoding by Manchester method. So here we propose 2 methods, the textual analysis and pixel-based texture analysis. For the interest of time, I refer this to my thesis more detailed. But in essence, the textual analysis is based on machine learning. We have clustered the blocks and then train the system to label blocks based on this likeliness to cause flickers. But then the pixel-based texture analysis is purely based on the variation of intensities of all the pixels inside the block. A large variation of value would indicate the more texture region. So the texture analysis is more accurate in identifying the blocks that can cause flicker, but it is computationally heavy. So we only apply this method for static video, for example, advertisement where the screen content doesn't change. And then, but for the dynamic videos, that is the normal videos, we for each frame has to be processed separately. We use this pixel-based texture analysis for more lightweight approach. And then the third one, to avoid flicker caused by sockets at the boundary of the checkerboard blocks, we use the computer vision techniques called superpixels. What it does is that it helps identify the natural edges inside the each video frame to align the encoded region. And then next we implement the block superpixels hybrid encoding method as follows. So each video frame still being divided into checkbox blocks and also two superpixels. And then we find all the so inside each block we find all the superpixels that that completely fall inside that block, and then mark the pixels inside that superpixels to be the one that is decoded, and keep the other pixels to be the same. And this hybrid encoding method has the desirable properties. It ensures that there is no common boundaries between the encoded units, and it allows an easy block-based decoding method because there is no need to rebuild the superpixels map on the receiver side. So this is to illustrate what we are trying to achieve. In this video frame, the green parts are the pixels are being decoded, are being modulated. We can see that in the plane regions, for example, this road, there's no encoding, but the encoding only happens in the high texture area like this car or this building. And also we can see that there's no shape border between the encoded blocks, which helps a lot in reducing the flicker caused by sockets. So here's our experiment setup. Our experiment was done in an indoor office settings. We have a monitor that is set to 120 Hz refresh rate, and we then display the sample videos at 1280 by 720 resolution at the encoding rate of 120 frames per second. The camera receiver is an iPhone 6, and we use this iPhone 6 at the recording rate of 240 frames per second. The distance between the screen and the camera is normally 70 centimeters. So there are more details in the results in the thesis, but here I just want to highlight the performance of texture code with two previous work in Frame++ and highlight. This figure shows the output of all the methods. We use the same block size of 32 by 32. Texture code here was able to achieve 15 to 16 kilobits per second of output, which is higher than highlight. Frame++ has a bit higher output, but at the block size of 32 by 32, it introduces more visible flicker. The interesting point here is that the use of the hybrid method. This is the method where we use the texture code in the high texture blocks, and we also use the highlight in the plain texture blocks. So on average, this hybrid system is able to achieve 22 kilobits per second of output, increasing the output of texture code by 45% and the output of highlight by more than 100%. It is even slightly higher than in Frame++ without introducing flicker. So in summary, in this project we propose a spatially adaptive encoding method to provide more output and near zero flicker to embedded screen to camera communication. Looking back to the goal of the thesis, texture code helps reduce human attention because the code is invisible. This is also high speed, so only by looking at the screen for a few seconds would allow the cameras to obtain quite a large amount of information. This also has some aspect of security because the information exchange usually happens within a close distance between the camera and the screen. Now let's move on to the second system named iLight, which is using visible light for occupancy estimation and room activity recognition. So nowadays, building-wide occupancy detection and activity sensing provides many useful applications. In smart homes, it can control lighting, heating, and ventilation, air conditioning based on the activity detected. In elderly care, activity sensing allows quick detection of emergencies or changes in the routine of the elderly patients. Installs the statistics about the customer traffic are useful to develop an efficient advertisement placement and product arrangement. So there are different sensing systems for occupancy detection and activity sensing. One common system is based on passive infrared motion sensing, which detect the radiated IR energy from the humans. However, PIR sensors are sensitive to other heat sources like hot appliances, sunlight, and open windows, etc. And they also require line of sight coverage, which means that more sensors are needed to cover an area. The second system is based on camera. Although they are effective and are used frequently in public spaces, camera raise privacy concern because when we use it in residential areas. Recently, Wi-Fi based activity sensing systems are also proposed, but currently they work with only small number of users and face challenges when scale to buildings with high number of occupants. Other approaches for activity sensing are based on smartwatches and smartphones. However, these approaches require users to carry or wear the devices. And recently, there is a growing interest in using visual light for activity sensing and localization. The advantages of visual light-based approach are that it is more privacy preserving compared to the camera, and it can leverage the dense lighting infrastructure already available in buildings. And we propose a system called iLight that uses only the currently available lighting infrastructure to do occupancy estimation and room activity recognition. So we equip each light with both transmitting and receiving capability so that they can communicate with each other through the light reflected off the floor. By doing that, we can build an opportunistic mesh of virtual light barriers from only the light bulbs on the ceiling. And then a person moving in the room would cross these invisible light barriers and can be detected by the sensors on the ceiling. In order to realize the iLight system, we will need to address two challenges. The first one is that each sensor needs to identify which light bulb caused the shadow observed on the floor, so that we can identify which transmitter and receiver link the user is crossing. The second challenge is sensing a much weaker reflected light from the floor, so we need to build sensitive light sensors for this task. Before we go into each challenge, let's briefly go over the components of iLight system. So all the light nodes would have a common mains power, and from this we derive the synchronization signal, so that all the light nodes will have the common time reference. And this time reference is then used for the light modulation module, which controls the LED light to send the signal without affecting the illumination functionality. And this time reference is also used for the high sensitivity photo detectors, which collect lights from multiple photodiodes being placed around the light. And the readings are then sent by a wireless transmitter to a central building server, and this server will run algorithms for localization, occupancy estimation, and room activity detection. So let's start to address the first challenge. Give each light source an identification code. So all light nodes here will be connected to the mains power, which is a 60 Hz AC signal. And by doing zero crossing, we are able to divide time into 8 millisecond cycles. And then we divide each cycle into many time slots, and then assign each light node a specific time slot. For example, this light is assigned time slot number 2, and what each light node does in this own time slot is that it turns off the light at half the time slot and remains on for the rest of the cycle. So this way of signaling has several advantages. It is periodic, and the frequency is above the flicker perception of the human eyes. So, and also the brightness is only reduced by a small amount. So with this technique of coded light signal, the light node would be able to send its own signature while preserving the illumination property functionality. So now we address the second challenge, which is building the sensitive light sensors for weak light reflected off the floor. Since the sensor needs to detect a fast modulated signal under 1 millisecond, we use the photodiodes as the first component because of its fast rise time. And then, but the current generated from the photodiode is very weak, so we first use a preamp from the transmitting impedance amplifier, and then a second amplifier stage by an instrumentation amplifier to further boost the gain. The output is then read by an ADC inside an MSV432 microcontroller. So here's an image of the receiver prototype. One thing to note here is that we placed a 4 cm aluminum tube to narrow the photodiode's field of view so that we can localize the users more precisely. In practice, this tube can be replaced by some lens to narrow the photodiode's field of view. So we have two algorithms for tracking users moving indoor, one for coarse grain tracking and one for fine grain tracking. Let's see the coarse grain tracking first. So here we have two neighboring nodes on the ceiling. Each can do the signaling and also has some receivers for sensing light reflected off the floor. Beside these two light nodes, we have some ambient light sources, for example, natural light from the window or other lamps. For this receiver, because of its narrow field of view, it can only see the light reflected off this small spot on the floor. So here, this is the light level for the normal situation when there is no user near in the view. But when the user is near this spot, he can block some light from other light source, so causing the reading to go out of the base light level. So this SPICE algorithm works by detecting the signal change outside the normal range. But that means that the possible position of the users can be quite large. In this figure, the users in any of these positions can cause the signal to go out of the range. So the possible position can be quite large. We can do better than this by taking advantage of the coded light signals that we presented before to identify exactly which transmitter and receiver link is the user is crossing. The time scale here is in second, but if you look at the scale of 8 millisecond cycle, we can get more valuable information. So that's how the second algorithm, named the delta algorithm, works. So let's zoom in the cycle level of the received signal. Here we can see that this receiver is able to see the dip from this own time slot 1, and also the dip in the received signal from the time slot 2 from this node 2. The delta algorithms works by measuring the difference between the received power, signal power between the on and off period of each time slot. By doing this, we can eliminate the effect of other light sources, and only concentrate on a single transmitter and receiver link. And this figure shows the delta measurements over many cycles. And when the users blocks the light coming from node 2, you can see that the delta values will go down. And by doing some thresholding, we can detect this crossing event. And because this detection only checks a single transmitter-receiver link, a detection event can result in a shorter possible range of user locations. So here's the picture of an I-light node. The transmitter is an off-the-shelf LED bulb. We placed 4 receivers surrounding this bulb and pointing to different directions. On the prototype, there is also an MSP432 microcontroller and a power board to provide power to the whole light node. So to evaluate the algorithm, we set up a testbed in this conference room with 6 light nodes on the ceiling. And a ZF camera is placed in the corner of the room to record the ground truth. And this is the localization error for the single person tracking scenarios. For SPICE algorithm, we are able to achieve median error of 1.18 meter, and this algorithm covers 94% of the time. And for delta algorithm, we achieve lower localization error of 0.89 meter, but this algorithm only covers 69% of the time. So there is a trade-off here between the coverage and the localization accuracy. So we try to combine the results of these two algorithms and achieve a median error of 0.94 meter with a better coverage. We also explore iLight's ability to do room activity and occupancy estimation. We use the readings from all the receivers in the room, and for each receiver we use the 12 average readings of the 6 time slots, including the on and off periods of each phase of each time slot, and we combine the readings of 4 receivers inside each line node and combine the readings from all the line nodes. And these readings are collected with the labels of room activity and room occupancy. And we train an activity recognition and occupancy estimation classifier using AWS ensemble classification.
Could we go back to your experimental setup there? So actually, the next slide. So how are you determining that person's position during your experiment?
In the ground truth?
Yeah, like,
Yes, so here I have the depth camera here, so at the point of the time of the experiment, I put the depth camera here and just scan the whole, so that would measure the distance from the camera to the person.
Okay.
And then from that, we build the ground truth of the room in the.
and the depth camera's accuracy is much less than the accuracy of your algorithm, right? In other words,
Yeah, so that is
what's the accuracy of your depth camera?
Much more accurate.
Yeah, that's what I meant. Like the error bar is much
The error
less.
bar is small.
So what's the accuracy of the depth camera?
The depth camera,
Centimeters?
yes, like 10 centimeters. That is what is said in the data sheet of that Z camera.
10 centimeters?
Yeah.
Another question, does it depend on who is the person in the room? Because Marco blocks a lot more than I do. I mean, in a sequoia tree and my little bush, that's the difference here.
Yeah, so-
Does that affect the accuracy? I mean,
Yeah, so I think that is
Geometry.
one thing we just average the height of the person to be some average height, but that is the short and the very short height.
I don't understand that. So, who was the person walking through the room, and what do you mean by average? Did you have more than one person walking and collecting that CDF?
Yeah, so we have multiple persons, the authors of the paper, and also we collect data for normal meeting scenarios. So there are, of course,
Okay.
there are height from different persons.
So real meetings with multiple
Ivan.
people.
Meetings, yeah.
He's also a sequoia. But the point is, it wasn't just you and
No,
being the
it's
person.
will
It
be
was
everyone in WINLAB. So
Okay.
so this is the first one is localization error. I remember this is only some of us doing experiments, but then from the next activity is only different scenarios. So we also consider that. But yeah, the height we haven't really specifically considered in this project.
Okay.
Yeah.
All right.
So you have like, as we indicated, do you have like a study of the different size of people, how they affect?
No, that is not in this project. Yeah, so the readings here are collected together, and then we sent to the building server, and then we train some activity recognition and occupancy estimation classifier, and this is a list of the room activities and room occupancy levels that we are trying to classify. So we evaluate the two classifiers by a tenfold cross validation over the whole data set. These are the confusion matrices for room activity recognition and occupancy estimation. So the overall accuracy of activity classification is 93.78%, and the average accuracy for room occupancy level is 93.7%. Okay, so in this project, we propose a device-free indoor tracking, occupancy estimation, and room activity recognition system that can be integrated in the lighting infrastructure. The key idea is that we construct a mesh of virtual light barriers, which is entirely set up on the ceiling. Now, looking back to the goal of the thesis, this light doesn't require any instrumentation on the users, and the signaling mechanism of the light is imperceptible to human eyes. Therefore, this method is unobtrusive to users. So Now we are moving to the second communication and sensing modalities, capacitive coupling.
All right, so technical question. Both this topic and the prior topic where you were looking at flicker, you've mentioned imperceptibility to the human eye. How do you quantify that?
Yeah, that's
Right,
the-
and in particular, I mean, there's deep like physiological science understanding the temporal response of the human visual system. So clearly what you're trying to do is operate below the response rate.
Higher
Or
than
higher than,
the-
you want to operate higher than the response rate, meaning that you don't want to activate, you know, you don't want to get through the smoothing filters that our eye uses.
Mhm.
So what is like the sort of the frequency cutoff for our
Yeah,
eye's visual system?
So the flicker perception for the light from the literature, I think there are a large literature on that. So I think the cutoff flicker perception frequency is from the human eyes is 100 hertz. So anything that is above that is, of course, there's some people that is the eye is more sensitive. You can detect the flicker, but for the previous experiments, the previous project is. We don't have the specific like subjective measurement, but for this one we run the experiments for many days with many people in this room doing different activities, and yeah, I think at that time we asked if that caused any flicker to person, and there is no like official measurement of perceptibility of the flicker. But from what I asked people, they didn't cause any flicker perception for the users. So yeah, but for the questions, probably from the literature, the cutoff flicker perception frequency is 100 hertz, and anything higher than that is most likely to be unobtrusive to users.
Anything higher than 100 hertz. Okay.
Yeah. Okay. Okay, so let's the motivation for this project. So nowadays we have increasing number of devices from small Amazon Dash buttons, a TV remote controller to the smartphone tablets that we use every day. In many cases, the interactions between us and these devices will be only a few touches before we move on to another task. So conventional user identification and authentication solutions, such as password or fingerprint sensor, will quickly become an overhead to users. In addition, there's a common need for multiple users to work on the same device, for example, in workplace and in hospital and in classrooms. Ensuring authorization and accountability is particularly challenging in these environments. So for these usage scenarios, it is desirable to have a convenient yet secure user identification and authentication technique. The current user identification and authentication techniques have several disadvantages. Some of them using IF or NFC, which is vulnerable to man-in-the-middle attack or the eavesdropping, because it's difficult to confine the signal considering the omnidirectional characteristics of the wireless signal. And there is previous work on authentication techniques based on touch, but they have low data rate and so insufficient to authenticate a short touch. And recently, there is research on using vibratory communication to transfer credentials from a wearable token to another device by using vibration signal through the human bone. This method has high data rate and is able to associate users' credential with every touch, but it requires significantly high power consumption as a result of using physical movement of the motors. So in order to create more convenient and low complexity solution to secure quick touches, we start with two important observations. The first one is that nowadays we increasingly use wearable devices such as wristband and rings. These devices are good for storing users' credentials because there is less chance that the user will misplace them, and they have a nice property that we are going to use is that they have in close contact with the human body. The second observation is that most interactions with the devices are through touch, so the human body can create a temporary connection between the wearable and the device. That leads us to the key idea of this work is to create a body-guided communication system that can transfer the code from the wearable device to the touch device. It will have several advantages. First, it confines the signal to only a few centimeters around the hand. Second, it can achieve the high data rate enough to transmit a complete authentication code on every touch. Third, it can do so with low power consumption. A closely related research is on body communication because it has a similar goal of transmitting a signal from one body part to another body part. There are two coupling types normally used in on-body communication: capacitive coupling and resistive coupling. In both these coupling methods, the transmitter and receiver requires two electrodes. In capacitive coupling, one electrode is in direct contact with the human body and the other electrode is left floating. And in resistive coupling, the two electrodes are in contact with the human body. So in capacitive coupling, it requires a capacitive coupling return path between the two floating electrodes. So the path loss is much more dependent on the surrounding environments, which is not a desirable property. So that leaves us with the resistive coupling options. So in resistive coupling, most of the signal will go between the two electrodes of the transmitter, but a small portion of the signal will go across the two electrodes of the receiver and it can be picked up. The properties of the resistive coupling is that the received signal will decrease with the distance between the transmitter and the receiver, and the received signal will be higher when the inter-electrode spacing of transmitter or receiver is longer. So there are some challenges in applying resistive couplings in our problem of transfer a signal from a wearable token to the fingertip. First, because the fingertip is small, we can only separate the two electrodes touching the fingertip by a few millimeters. This significantly reduces the receive power from these two electrodes. Second, it is not desirable to require all touch surface to be made of conductive materials. In most cases, the electrodes could be more easily hidden behind layers of non-conductive materials like plastic or glass. This means that there is no direct resistive contact between the electrodes and the finger. So body-guided communications can overcome these challenges. The key difference in our design is the combination of direct skin contact at the receiver, the transmitter, and the double capacitive coupling at the touch device. So the two electrodes in the wearable are powered by AC signal generator and placed in direct contact with the skin. So inside the human body, there's conductive tissues which are separated from the electrode by skin's epidermis layer. And we model this epidermis layer by a pair of resistor and capacitor. We also model the impedance between the point A and point B underneath these two electrodes. So most of the current will go between these two electrodes, but a minor path, a second much weaker current path, will go through this finger and through the touch device. And this path can be modeled by the tissue impedance between the point B and the fingertip and the two capacitors CFF and CX. CFF is the capacitor between the fingertip and the front electrode, and CX is the capacitors over the air between the reference point and the last body area. Then this CX will connect with the last impedance, body impedance with point A and effectively closing this circuit. By experiments, we found out that when the finger moves away from the touch surface, this CFF will have the highest impedance on this minor path. This is because of the high permeability of the air and the small size of the fingertip and the front electrode. The high impedance of the CFF will effectively cut off the current going into this path. As a result, we can achieve the touch association needed for the touch authentication. So we made several prototypes for this body-guided communication in the form of form factor of a wristband and the ring. For both of them, we placed two thin copper strips on the two sides of the wearable to maximize the spacing between the two electrodes. And for the design of electrodes on the touch device, we chose two example designs. One is the one is the button design for small IoT devices like this Amazon Dash button, and one for the phone with the touch screen. So for the IoT button, we embedded an electrode behind the front-facing plastic, and then for the phone, we put a bigger electrode on the back of the phone. And the receiving electrode is connected to a receiver. We chose 150 kHz carrier wave, and the user identification code is modulated on this carrier wave using on-off keying modulation. At the receiver, we would like to use a common microcontroller to demodulate the identification code in real time. So considering the limitation of the microcontroller in terms of memory and speed and sampling rate, this receiver will now convert the 150 kHz to 5 kHz, and the 5 kHz signal out after this low pass filter will be read by this microcontroller in real time using dual buffer memory and ping pong DMA. So as an illustration, this figure shows the signal received from the receiver board. And in this experiment, the user wears the wristband with the transmitter board on the wrist and touches the receiving electrode multiple times with the same hand. And the transmitter continuously modulates a 128-bit identification code using on-off keying on top of the carrier wave 150 kHz. And we can see that the amplitude of the output 5 kHz signal significantly increases during the time the user touches the receiving electrode, and is weaker when the finger moves away from the electrode. So when zooming in this red area, we can also observe the identification code sent from the user with on-off key modulation. So the channel in body-guided communication highly confines the signal and protects against eavesdropper. We measure the received signal at an adversary receiver with small distances from the transmitter and compare with the received signal at the intended receiver. Here, these blue lines will show the received signal at the intended receiver and at adversary receiver at the transmission voltage of 3.2 volts. We can see that the signal at the intended receiver is higher than the adversary receiver, and the signal at the adversary will decrease over the distance. As we decrease the transmission voltage, both the signal at the intended receiver and adversary receiver will go down, and at the transmission voltage of 0.4 volts for the adversary, the received signal will go below the noise level just at 1 centimeter. But the signal at the intended receiver is still about 20 dB above the noise. So it shows how the body-guided communication channel is protected against the remote monitoring. 2,000 touches over 5 days, and with different touch duration and different code length. The data rate is 1 kilobit per second. This figure shows the decoding success rate versus the touch durations. For all the code length, the decoding success rate increases as the touch duration becomes longer. Also, for the same touch duration, shorter code will have a higher decoding success rate. But for a common case, for 128-bit identification code, this body-guided communication achieve 100% accuracy for any touch longer than 300 milliseconds. That means most of the time, the receiver can authenticate the user. The third advantage of our technique is low power consumption. The microcontroller in the hardware token only needs to continuously modulate the user code using on-off keying, so it can be operated at low power. So our current prototype using MSP430 microcontroller in its low power mode is able to achieve 3.9 milliwatt at the data rate at 1 kilobit per second, which translates to 3.9 microjoule per bit. To put things in perspective, the only communication method with the touch association capability, vibratory communication, can achieve that at 100 microjoule per bit, which is 2 order of magnitude than this body-guided communication. And for the RF and NFC, because of its high power optimization, it can achieve the order of 10 nanojoule per bit, but they cannot do touch association needed for touch authentication, and they are also susceptible to eavesdropping. And also, the last thing is that we also discussed in the thesis about the theoretical limit of how low power this token in our technique can run, and calculated that it can achieve the 90 nanojoule per bit which is only a bit higher than IF and NFC. So we propose a body-guided communication method for securing every touch interaction from users with a variety of devices such as phones or Amazon Dash buttons. We have shown 3 advantages about technique. It is more secure against eavesdropping. It has low power consumption, and it can provide robust per-touch authentication. So this body-guided communication matches the common goal of this thesis because it provides a fast and seamless and secure authentication services for users on their touch interaction with devices. The last project in my thesis is hand-sense capacitive coupling-based dynamic micro finger gesture recognition. The motivation for this project is from hand-mounted device for augmented reality applications. These devices are transforming modern workspace thanks to their ability to overlay digital information on the physical world. There's a growing number of practical applications in different industries, for example, image-guided therapy, manufacturing, construction, and training. However, it is challenging to provide input to these devices while being user-friendly and intuitive, and ensuring the immersive experience of these devices. So hand or finger gestures are good method for controlling these head-mounted devices. Current technique for capturing hand or finger gestures, including using camera and computer vision, or putting inertial sensors on the fingers, or impedance tomography by wrapping a band surrounding the user's hand. However, these solutions have several disadvantages. Camera-based approach require the hand to be in the field of view of the camera, leading to users need to hold the hand on the air like this. Inertial sensors or impedance tomography requires heavy instrumentation on the hand. So, and for this method, gestures being recognized usually include last movements of the fingers or the whole hand, which can be tiring for users after a long period of use. So this solution is not quite suitable for controlling SMDs in working environments because, as we can see in the previous applications, hands are often busy in other actions, and so low effort finger gestures are more preferred to avoid the interruptions to the user's workflow. So we propose a system called HandSense with the following design goal. It should be lightweight, both in terms of hardware and software processing. It should be always available and not constrained to any reason of operations. And it will be able to recognize dynamic micro finger gestures that are suitable for controlling SMDs. So the key idea in HandSense is capturing the pairwise profiles of capacitive coupling between the electrodes placed on the fingertips. The capacitive coupling between the electrodes will help inferring the spatial relationship between the fingers. And given the structural constraint of the human hand, this relationship will allow recognizing micro finger gestures. Another point is that gloves are used in many workspace application of augmented reality, and so the electrodes can be integrated in those in the fingertip section of those gloves. And the electrodes are the only sensing elements needed in HandSense, making the system low cost and not intrusive. The second component in HandSense is the central controller board called card profiler, which can be worn on the user's wrist. This design allows the user to use his own smartwatch or wristband and connect with the glove, and then to use with his own head-mounted device. And this card profiler board will require minimal hardware and performs a lightweight pairwise capacitive coupling measurement technique. And then this card profiler board will send over Bluetooth the measured time series signal of the capacitive coupling to a remote host, and this signal sequence will be passed through a neural network-based classifier to classify into different finger gestures. So with this design, we can see that the system is self-contained and always available, and it will be able to detect fast movement and allowing low-effort finger gestures needed and highly suitable for controlling SMDs. So in hand sense, the electrode will act as both transmitting and receiving elements. In each link, one electrode is powered by an AC signal, and the displacement current is measured at the other electrode. The displacement current is proportional to the capacitive coupling between the two electrodes, and this capacitive coupling C, it depends on the plate area and the distance between the two electrodes. However, we faced a challenge when putting electrodes on the fingertip, because the large amount of coupling between the two electrodes actually happen through the hand as opposed to over the air. Because the hand is more conductive than the air, it is difficult to measure the small change in capacitive coupling through the air. On top of that, a large capacitive coupling to the hand. So to solve this problem, we proposed a two-electrode design in which we add a ground electrode underneath each signal electrode to minimize the capacitive coupling between the signal electrode and the hand. And these are the received signal for two distances when the distance between the two fingers are 3 centimeters and when they are touching each other, and for the two designs, 1 electrode and 2 electrode. Here we can see that only in 2 electrode design there is a difference between when the distance between the two fingers are 3 centimeters and when they are touching each other. For the 1 electrode, the received signal stays the same for both cases. So the second feature in hand sense is the lightweight capacitive coupling measurement technique. We first started with synchronous detection. The basic idea is mixing the received.
In the previous slide, I have a quick question there. So let me try to understand this challenge, right? So you're saying that the bike path going through the finger is the major path, right? And that is the challenge.
Yeah.
So do you have, is that, well, first of all, is the electrode connected to the finger? It's not, right?
So it is separated from the finger by a layer of the glove and some insulation tape in our prototype, so that it is not actually touching the skin but through the glove layer.
Okay, and if it was well insulated,
yeah,
will that still be the major path going back? And
yeah.
will you quantify that?
So when we did experiments, so when use the same 1 electrode design, we see that the received signal for both, the received signal will not change when we move the signal, even when touch, and when they are moving further apart, the signal doesn't change. So.
And because of that, you confirm that it going through the bike path more.
Yes.
Well,
so because we know the hand is more conductive than the air, we did some calculation and see that the impedance through the air is actually higher, lower than the impedance through the hand, to the air.
And so, why the technique that you propose here work?
So here, so for these 2 electrodes, here they won't have the same. So this ground layer won't separate. Will isolate the signal electrode from the hand surface, and also that so for each electrode on the fingertips, they won't have the common ground connected back to the ground of the wearable device, of the wristband.
Yeah. Okay, I'll ask more later.
Okay. Yeah, so first we start with the synchronous detection. The basic idea is mixing the received signal with the original transmitted signal and the 90-degree shift version of this signal, then doing low-pass filtering to obtain the in-phase and quadrature components, which are used to calculate the received signal amplitude. However, implementing this synchronous detection will require significant hardware costs, including the phase shifter, the mixers, and the low-pass filter. And also the low-pass filtering also make it slow to respond to a fast signal. So we move to the synchronous sampling, which seeks to remove these hardware components while still being able to estimate the amplitude of the received signal at the transmitted frequency. If the transmitted frequency is f, and we sample the received signal at 4F sampling frequency. We observe that the amplitude can be estimated by only 4 samples on one signal cycle using this formula. Although the hardware cost is low, the the problem is that the synchronous sampling requires sampling rate of 4F, which can exceed the capability of some microcontrollers when the transmitted frequency is high, for example 100 kHz. So to reduce the required sampling frequency, we move another step forward with synchronous undersampling. We assume that inside the small time window, signal is repetitive. So instead of sampling S1, S2, S3, S4 on the same cycle, we sampling them at continuous cycles. The sampling frequency is then reduced to 4/5 F. The formula to estimate the amplitude still stay the same, but with this technique we are able to have a frame of 10 link measurements between the fingers will take only 10 milliseconds. And these are the 3 finger interactions that can be recognized with hand sense. The first is direct over-the-air electrode proximity detection. So in this figure, we can see the received signal for all different links, and this gray box is one gesture instance. So here for this closed fist gesture, we can see that the signal goes up when the fingers are moving close to each other. And for this technique, in our prototype, the maximum detection range is only 5 centimeters. Second, we have the detection of finger touching each other. For example, in this index pinch gesture, when the 2 fingers touch each other, the capacitive coupling between the 2 will be the strongest. This strong capacitive coupling will produce the saturated reading at the front-end receiver, and then that can be detected. Third, we have this indirect through the hand electrode communication. We observe that when 2 electrodes are touching the palm at the same time, because the hand is conductive, there is some capacitive coupling path through the hand between the 2 electrodes. For example, in this tap gesture, when these 3 fingers are touching the palm, and then this thumb touching these index fingers, so whenever it's touched, the received signal on the 3 links between the thumb and these 3 fingers are actually going up, and this is a feature that can be used for the classifier. So the input for the hand sense gesture classification is the time series data of data samples. Each contain received signal amplitudes in 10 links from the CAF profiler board. For this time series classification problem, we use several common neural network-based methods, in particular multi-layer perceptron, convolutional neural network, and long short-term memory network. I would like to refer the details of this network into my PhD thesis, but and also I would like to point out that these experiments with different machine learning techniques is only for the purpose of verifying the distinctive signatures of the collected capacity profile in inferring finger gestures. We are not trying to improve the performance of this neural network architecture. We design a capacity profiler board that can be worn on the user wrist, and then the user also wears a glove with the electrode attached on the fingertips, and these electrodes are then connected back to the CAF profiler board through coaxial cable. We also design a set of 14 dynamic micro finger gestures as being shown here. These gestures are highly suitable for operations for hand-mounted devices. They also demonstrate the capability of hand sense in recognizing the finger interactions described before. Most gestures require only a small amount of motions and can be performed by only muscles controlling the fingers. There are a few challenging pairs of gestures, for example, sliding from left to right or sliding right to left, or not turn clockwise or not turn counterclockwise. So the final result is that MLP can achieve 0.9 precision recall and F1 score, which is a good baseline for classification. So even with simple fully connected layers model, the distinctive signature in the capacitive profile is already able to provide reasonably high accuracy. However, we see some misclassification between the closed pair of gestures, for example, sliding left to right or right to left, because MLP lost all the temporal dependency information. CNN performs a little bit better, better than MFD at about 94% of precision recall and advanced score. This is because CNN gives the 2D data as the input to the network, and its 2D filters are able to learn the temporal dependency within each link as well as across links. LSTM performs even better at about 97% precision recall and advanced score. We hypothesize that this is because LSTM has better memorization of the long-term dependencies than CNN. So overall, these networks provide high gesture recognition performance, proving that the distinctive signatures in the data stream already able to provide a high accuracy classifier. So in summary, we propose a system based on pairwise capacitive coupling measurements between electrodes, based on pairwise capacitive coupling measurements between electrodes, based on fingertips to recognize dynamic micro finger gestures. These include an electrode placement configuration to reduce the effect of the user hands on the measurements, and the lightweight measurement techniques based on synchronous undersampling to capture the high resolution capacity profiles. We believe that hand sense is an intuitive, low effort finger gestures recognition for users to better experience augmented reality applications in the workplace. To summarize the thesis, I have worked on different communication and sensing methods for seamless interactions between users and their environments. The two modalities in use is visible light and capacitive coupling, which are ubiquitous in indoor environments and on human body. The communication techniques, including texture code and body guided communication, are well aligned with users' intentions, including where the users look at and where the users touch. The sensing techniques, including eye light and hand sense, have low complexity and overhead. Looking ahead, I hope that the design points in this thesis can help push the ubiquitous computing toward wider adoption. The human-machine interface should be more intuitive, requires minimal instrumentation of human body and environments. And the design should have a built-in security and privacy primitives for the ease of mind for the users. So this is the list of my publication during my PhD. Lastly, before we come to the question session, this last slide is a thank you note to all the wonderful people that were with me during my PhD years. I want to thank my advisor, Professor Marco Bruteser. Marco has taught me a lot about identifying research topics from practical problems, and also always had the bar high for research quality and delivery. And Marco also gave me a lot of support during my PhD, my research career at Rutgers, and also a lot of career advice for the choice after graduation. Thank you, Marco, for being the best advisor that I can ever hope for. Yeah, and I'm also grateful for the opportunities to work with Professor Rich Howard in many projects. Thank you, Rich, for being generous in time whenever I come to you with questions on physics and electronics that are beyond my knowledge. And thanks to you, I understand the value of working from the first principles and how to break a complex system into smaller components so that I can understand what is going on. Yeah, I think that these lessons will be very helpful for my future. I want to also thank Professor Nguyen Chen, Wei Trapi, and Dan Wu, who gladly accepted to be on my PhD committee. Also, I want to thank all my collaborators who it's so fulfilling to work with so many smart people with different research perspectives. And thank you all WINLAB friends for your help in formulating ideas and helping with experiments and provide feedback for my PhD work. And lastly, I want to thank my wife Chang and my son Ted for their support all my PhD years. And with that, I want to conclude my talk and open to the questions.
Thank you.
On the hand sense, were the errors clustered with individuals, or were they spread out among the 10 users? In other words, there were 10 users that you did those studies on.
Yes.
There are some misclassifications. Are they clustered In other words, do some people have differences in their physiology that makes them more prone to errors? Are there differences between the people, or are the errors just spread out throughout the group?
I think we don't have the official look at the data, but I think for some data, for some people with longer fingers, I think the signal would look differently, much more differently than the other, the signal from other people. So I think that the error can, for some specific people, it can be more than the other people.
So you might be able to develop a criteria for what works and how you would modify it for other people?
I think one thing to improve the accuracy is that per user training. So one person can have this device and then train it, maybe a few rounds. And we actually figure out in the paper that we can train the system on using one glove, and then when we change to another glove, the system still has a high accuracy. So one thing to work to improve the accuracy for this is that per user training, and that will improve the accuracy of the system.
Any other questions from the audience?
So when you use the eye light, right, you do the human movement monitoring, like, can you count how many people are in the environment?
It is difficult to give an exact number of people in the environments, but we only classify it into different level of occupancy, like yes, different levels. So nobody in the room, 1 person or 2 person, and then more than that, probably it is for the purpose of the meeting. So we only classify to that level, 0, 1 to 2, 3 to 5, and more than that. But there's only 4 levels of occupancy in our system.
Okay. So what are the 4 levels? Like
0,
0, okay, 1.
1 to 2, and 3 to 4, and then more than that. Then, yeah.
Okay, I see.
1, 2,
But
3,
when you-
fit.
But when you define 2 to 3 and 3 to 4, how do you define those? Like, depend.
Yeah, so I think that
If the people they stay close to each other, right? It's not like do you know like what's the boundary? Like if they stay closer to each other, will your classification system get confused?
I think that is some cases that I cannot detect, because if 2 people are close to each other, they have the same
The word overlapping the
overlapping, and that
shadows,
I cannot be detected. Yeah, so I think it's 1 to maybe 2 people. It is it's only accurate when the 2 people are spread. Like one person sitting here and the other person sitting there, and they will have 2 different shadows on the floor. And in that case, I like to detect. But if they stay close to each other, then the shadow is overlapped, and in that case, it might cause some difficulty to
So
highlight.
that will like depend on like how many lights you have on the ceiling, right?
Yeah.
Then
Yeah.
you can determine
So
the
in our
density of the lights. And,
Yeah, so in our system, we also
Overlapping
evaluate
of
the
the
number
shadows.
of lights too, and figure out that the distance between the light can be up to 3.5 meters before. But any distance longer than that then cause difficulty, because the light would be travel at a further distance. So the sensor would have difficulty in detecting the shadow in that case.
Okay, then we'll exclude the audience. And are there more questions from Viet?
Quick close question, so once all, you guys, maybe this is a question for you, Rich, but when we go to the visual, the light flicker, localization,
Okay, sorry.
The light flicker.
the localization.
Oh, yes, yes.
I like.
Yeah, I like.
Okay.
So maybe a picture of the signal where you're modulating. All right, got that one. Previous one will do.